Well, thank you very much, and thank you for the invitation to give this talk. So I will try not to be too hardcore. As it should be apparent from my title, I will try to talk a little bit about what we normally call structure-function relationships, which are important not just in inorganic chemistry, but all over chemistry. So, but before I do so, I was asked by our host, Jens Christian, to talk about my career. And I was a little bit hesitant when I heard this suggestion because you can ask, does such a thing exist? But then I decided, well, a bad example is also an example. So for those young people who attend this and listen to this, I will give some examples of what you should not do. So I have, this is my map. So normally you see these maps where people travel all over the world. You can see I moved approximately 18 meters from the lab side to the office side of this building here. I started doing my BSc here in Copenhagen, and that went kind of okay because I did the things I should do. I passed my courses and did so okay. Then I did my master's in the same section as I did the BSc. I spent more than 5 years on my master's. This is not recommended, so that will not work nowadays. I did interesting things, but also very long-winded things. So I made papers which required 7 referees to be passed during this time here, but I enjoyed myself and there was no pressure to finish. Then I did my PhD with the same supervisor. That's of course a no-go. And I did a PhD with absolutely no publications with my supervisor, which I guess is also not the way to go. Then I did my postdocs, and what is clearly wrong about those is I had absolutely no focus. I went to Warwick to learn something about DFT calculations, which at that time could not really be applied to my systems here in Copenhagen. Then I went to the Max Planck Institute for Strahlenchemie in Germany and did some magnetism and synthesis and spectroscopy there. I went to Caltech, broadened my spectroscopic toolbox a little bit, and did also some synthesis and catalysis there. Then I went to Israel, to Technion in Haifa for a short stay, and then I went to Bern in Switzerland and did some, that was hardcore modeling of vibronic couplings. And then I was called back to Denmark. And you know, in academia, if you're called back, it means an academic call. This is really very prestigious, but there are other types of calls, those types of calls. So I was instructed to get my butt back home and stop fooling around. So I procured some money from the research foundations and eventually got a position here. So depending on your inclination, you can view my career as the first or the second sign, and I would say both are to some extent applicable. Certainly my current interests are best described by the second of those signs down there. I have not really been able to focus since I stopped my postdoc, so I have been interested in fundamental coordination chemistry of small ligand systems. So I've been looking at small ligands like oxide, nitride, and carbide bound to metal centers. This has never been funded, but it is a recurrent interest with me. And if you want to learn more about coordination chemistry of carbides, you can go to the lunchroom and look at the chemical reviews, which is up there. Then I've been interested in molecular magnetism, in computational modeling, in structural chemistry. So you will often see me swearing in front of the diffractometers in the cellar. And we've recently tried to broaden the range of structural chemistry techniques available by applying for an electron diffractometer from the Novo Nordisk Foundation. Then I have gained some interest in lanthanide and actinide chemistry, the FLOC, and I have some industry collaborations relating to magnetism and magnetocaloric effects. So I'm not going to talk about all this today. So today I'm going to try to bridge some of the molecular magnetism with lanthanide and actinide chemistry and the structural chemistry. And The core assumption here is that there exists structure-function relationships, and in order to do something which we call design, we need to be able to control structure. The good thing about being an inorganic chemist is, of course, you have the full bingo card to play on. So you can pick your elements for redox properties, optical properties, or magnetic properties. And so far, I have not limited myself. As you can see, I've been pretty much waiting all over the place. And that's, of course, one advantage. So what is the disadvantage then of being an inorganic chemist? That's quite clear if you think a little bit about it. It's lack of control. So I'm sure that Michael is nodding right at the moment, but yes. So normally we draw this closed circle. So we do some synthesis, we characterize our systems, we do the modeling, and then we, based on the knowledge gained, we design new systems, and then we synthesize them. But the lack of control is in the last part of this circle here for an inorganic chemist. And I guess that in the chemistry community, the situation is perceived a little bit like this here. So you have, I think it's Knud to the left, and you have let's just call it a generic preparative inorganic chemist to the right. I mean, so we don't have the level of control we really want to have. And the question is why? What's the goal for a preparative chemist? And I'll give you 10 seconds here to think about what molecule I'm about to show. So those of you who have seen this before are not allowed to participate in the contest. But of course, if you want to be a real preparative chemist and have control, this is what you want to synthesize. This is mitotoxin. It has 99 stereo centers. It has taken 160 man-years and it's not yet completed. But the key point is organic chemists, they do this. Inorganic chemists are not nearly as ambitious. And why? So I'm sure some of my colleagues will say that's an inherent difference in skills, but it's also something you invariably pollute your research with when you broaden it all over the periodic table. And that is, you have a much larger variety in bond strengths, and attaining selectivity is much more difficult. So how can you get the level of control which organic chemists have? So what organic chemists have, they have orthogonal reactions, so they can do something at one end of the molecule and not destroy it at the other end. So we don't want to hit too hard in our synthesis. And then the other key point is many of their advanced molecules are made by convergent synthesis. So you make building blocks and assemble them. So the idea is that we can gain some level of control by doing something similar in coordination chemistry. This is just an example of one of the convergent steps in the mitotoxin synthesis. And you have seen a nice example of convergent synthesis. I hope at least all attendants here also went to the annual meeting of the Danish Chemical Society, where Jonathan Nitschke presented this wonderful molecule of the year. And clearly here is a convergent synthesis, an assembly guided by the metal ions at the corners of this tetrahedron. So is this something we can generally do? I mean, can we just take a rigid ligand like we have here, so these extended arms bridging the ion centers, and use those to guide the structure we want? And it's not really such a general approach, because if you have interests apart from the center of the D block, you also are challenged by the fact that the metal centers outside the middle of the D block have much more variability in terms of coordination geometries. So for example, if I ask you, if I take this fairly rigid polydentate ligand there and try to stitch something together using a lanthanide, you can use different lanthanides, and this is the product, and I couldn't have predicted it, neither could any of you. I mean, you're lying if you claim you could have predicted this. So obviously, we cannot just emulate the nice Nitschke chemistry. So we need to be a little bit more modular than that. And one thing we can think of is to use pre-assembled metal complexes as building blocks, as sketched here. You can say maybe this Lego metaphor is not the most appropriate one in the world, because you can make things which are quite messy to look at, also using Lego. And maybe you're not steering your assembly well enough if you just use the Lego metaphor. But it's nevertheless an approach which we have wanted to take, use building blocks and assemble metal complexes. And one of the things we realized was that, well, there is a structure directing motive if we go to one of the small ligands. And by the way, one which is isoelectronic to my key interests in carbide, nitride, and oxide, namely fluoride. So fluoride is different from chloride, and you can easily see this if you have taken one of my courses, or if you look at these two compounds which have the same stoichiometry, but obviously quite different structure. And the key point here is, if I can do this now without, so the key point here is that fluoride only form linear bridges, or have a very strong preference for linear bridging, whereas chloride is much more forgiving with respect to bond angles when it bridges between metal centers. So the idea was to use fluoride to steer geometries, and we can do that and attaching to fluoride either protons or cadmium metals, 3D elements, 5D elements, 4F elements, and it works broadly. So I'm just gonna give two examples from 3D elements and from the 4F elements. So among the 3D elements, here is a sketch of an example with a linearly bridging fluoride. It's between two manganese 3 centers. And the important point here is that even though one could come up with good theoretical reasons why fluoride would be a bad mediator of magnetic exchange, it's actually not. So the magnetic exchange we see here is quite strong. And we can unravel the electronic structure of this system here, not just by looking at the magnetism, but we can look in more detail, for example, by using a technique as inelastic neutron scattering. So this here is, for those of you who have not seen an inelastic neutron spectrum before, this is just a Raman spectrum at a different energy range. So in the middle you have the high peak, which we're not interested in. It's the analog to the Rayleigh line when you scatter light. But now you scatter neutrons and you can lose and gain energy, and you can really map out in great detail the electronic structure of your system. And this nice property of neutron spectroscopy is something which also made us interested and involved in the so-called QMAC, which is a new lighthouse funded directly by the ministry. And it bridges a lot of different institutions, but it has Kim Lefman at physics here at the NBI as the central person. And we do gear up to try to exploit the ESS in Lund when that opens. And we'll get a new colleague based on this center, I should also add. So if we go from the D block, from manganese to lanthanides, the F block, then we're faced with some challenges. So you can see here some F orbitals, or actually all of them, and you can see from a distance they look almost like spheres. And the higher the L quantum number is, the more spherical the orbitals become, which means they also become less sensitive to the surroundings in terms of angular variations. So it's difficult to design things. And furthermore, these orbitals are buried, so they don't interact very well with the ligands. So that has as a consequence that the F block elements, especially the lanthanides, are kind of promiscuous in terms of coordination numbers and coordination geometries. You cannot predict what you end up with, as we saw earlier. And there are not many easily exploitable bonding preferences, but they are so-called hard ions. That means they are fluoride fans. For example, if you go into nature in Sweden, you can find bestnäsit, which is a mixed fluoride carbonate of lanthanides. And that means that we could take the toolbox we had before and reuse the fluorides. And doing that, we can make a whole zoo of polynuclear complexes combining lanthanides with transition metals. And from this whole zoo, we started looking at some of the simpler ones. And One of the simpler ones was one where we had a gadolinium, and that gadolinium was linearly bridging or almost linearly bridging to chromium. And then we had some DFT calculations performed on this system, and the interaction between the two magnetic centers here, that interaction was very well produced by the DFT. Of course, computational chemists like to play in the computer, and what was done was this molecule was bent. So taking exactly the same stoichiometry, but just bending the angle around the bridging fluoride all the way from 180 degrees, as was found experimentally, and down to below 140 degrees. And something interesting happens. So the interaction between the two centers become smaller and smaller and smaller as we bend the angle. And eventually we have a crossover between antiferromagnetic and ferromagnetic coupling, where there is no interaction between the two metal centers. So that occurs there around 140 degrees bonding angle. And you can say, okay, so that's not good. Don't you want magnetic interactions? Well, the good thing about magnetic chemistry is that you can sell your system no matter whether you have a strong interaction or a weak interaction. So in this case here, you have a lot of spins sitting on different metal centers, and if those spins do not interact, you have a lot of entropy. And this you can exploit in terms of so-called magnetic caloric effects. But the very nice thing about these calculations here is also that if we took the whole zoo of complexes we had before, and if we plotted this zoo here in with the experimental bond angles on this curve, which was only made for one compound, then we can see that this curve really does reproduce the behavior, even in the cases where we have managed to bend the fluoride bridges, which is difficult, but we have attained a 140 degree, almost 145 degree angle. So the conclusion is that BS is not BS. And that's of course a joke. So broken symmetry DFT, it's not bullshit. It does actually reproduce magnetic interactions quite surprisingly well for this class of systems. So what are they good for? As I said, they're good for the so-called magnetocaloric effects. So essentially this here is entropy changes as a function of temperature in various applied magnetic fields. The key point here is that our molecular materials here actually outcompete commercially used materials like gadolinium, gallium, garnet in terms of performance. They do have some drawbacks in terms of thermal conductivity, but they are actually quite nice, and we can save polar bears with these compounds because we can use them for cooling in the temperature range where we normally use helium, but we are running out of helium. So it's absolutely interesting from an application point of view. You can also use magnetocaloric effects to heat things, and this is something we have done together with Albert Topsøe. So building catalysts sitting on top of magnetic materials, and instead of heating from the outside, making inductive heating using the magnetics of the carrier materials. So do we have control? Well, maybe you can say at least we could argue that some of these many structures we produced with fluoride bridging could be rationalized. We're close to linear bridging in those cases where we didn't have. We could also kind of understand this. So, but all of those systems were potatoes, generic potatoes. They had no symmetry elements. And then you can say, well, symmetry and geometry, isn't that the same thing? And it's not. When symmetry and geometry differs, that's when you know that nature or whatever other higher powers you believe in don't like you. So you can try to build in symmetry in your systems, and sometimes it breaks when you crystallize things, and or it breaks by taking up solvent molecules for some reason. And you can say, so what? I mean, geometry is kind of an approximate symmetry, so isn't it good enough? But it's not. So you can see here a potato, and this is two magnetic axes in this molecule here, and the computed and the measured one are well aligned. That's all very good. But if you take a very famous family of lanthanide complexes, the so-called DOTA complexes, which you can get injected in your body if you go for magnetic resonance, at the hospital, then you will see that going across the series of delta complexes here, the easy axis of magnetization is all over the place. So it can be in the oxygen plane of this ligand here, or it could be perpendicular to the oxygen plane. But sometimes it's well reproduced by calculations, and sometimes the calculations are pretty much off. So, and that's a problem with having no symmetry. So what can you do to circumvent this? You can try to build in symmetry and also relieve yourself of the problem which is sketched here, namely the fact that the F block chemists are 93% more distressed than D block chemists. And why this precise number? Well, it has to do with the number of parameters you need in order to describe the electronic structure of these systems. If you look at all the different perturbations you have on free lanthanide ion, you have some interelectronic repulsion, which is dominating in some spin orbit coupling, then a ligand field, which unlike the D block here is less than the other perturbations. And then eventually you can put on a magnetic field, and this creates this whole hierarchy of splittings of your energy levels. If you have no symmetry, then for an F block system, you have 27 parameters. And you never had enough observations on such a potato in order to extract all these parameters, which means you can't understand the system. Of course, you can do an ab initio calculation. You can do a complete CAS-SCF computation on the actual system we're talking about, but that only provides you a description of that system. It doesn't give you any broader view of the class of systems you are investigating. So, but if you can crank up the symmetry, if you can make highly symmetrical complexes, then symmetry kills off a lot of these parameters. For example, if you can make D4D symmetry, then you're down to 4 crystal field parameters for an F system. Now we are suddenly in a range where we actually have a chance of determining the values of these parameters and hence understanding the complete electronic structure of the systems. So this is a goal. This is just an illustration of a situation where you have C4 symmetry, just a 4-fold axis here, and you have some parameters here which are called 4 plus minus 4 and 6 plus minus 4. That's altogether here 4 parameters. And if you raise the symmetry to D4D, those annoying beasts there vanish, and you only have 2, 0, 4, 0, and 6, 0. So illustrated here by a prediction made by Eugene Coronado from Malaysia. So the bottom line is, if we can make exact D4D symmetry, we kill some parameters, and those parameters are really nasty if you are interested in magnetism, because those are the ones which makes the so-called quantum tunneling of magnetization, which means that you magnetize your single molecule and it forgets that it was magnetized because it equilibrates between the different MS states that you have in the molecule. But if you don't have this quantum tunneling, you have a longer memory time for the magnetization. So you want to go for something of high symmetry. And in order to make some structure or use some structure directing building blocks, we stole something from Linda Dörr from Boston. She used these thioacetates bound to divalent metal ions from the first transistor series and anchored on a platinum-2 ion. So this propeller or this paddle wheel here has a platinum metal and a nickel bound, bridged by these two ends of this thioacetate. And then you can see something strange. These molecules dimerize, the platinums seem to form a bond to themselves. This is interesting because that's a kind of bonding which is not that common in coordination chemistry, but we might be able to exploit it. So we have this building block or structure directing motive, which we want to use. And we have some orthogonalities in terms of reactivity because we have a hard end, we have a soft end on the thioacetate, and we have the metallophilic platinum, which apparently likes itself to a quite extensive degree. So we have been playing with lanthanide complexes based on such ligands. And the nice thing about these are they are really very tunable. So we can play a lot, and even just playing with counter ions for these monoanions, we can do a twist of the angle So we can go from the D4D or close to D4D to some lower symmetries. And so you can see by choosing the right counter-ion, we get very close to a 45-degree twist in this cube here, which is the perfect D4D symmetry. The problem is that crystallography does not allow for a perfect D4D, or it does not allow you to enforce it. It does allow it, but you cannot enforce it by symmetry in crystallography. So you have to kind of engineer it chemically. Oops. So yeah. So this here we can play on, because we have this good conformation of our system, and then we can also make a twisted conformation where they are only rotated 22 degrees relative to each other, two sides of the cube. And what we can see is that the prediction by Coronado was correct. We win an order of magnitude in terms of magnetic memory time. So we have effectively actually quenched this quantum tunneling of magnetization. When we have all these parameters determined for these systems, we can use them. So we can take detailed magnetometry and inelastic neutron scattering, and we can determine these parameters really well. Please note that there are uncertainties on the points in these diagrams here. So we really know what we're talking about now. When we know that, we can calculate how does the magnetic properties behave. And they're kind of interesting for these systems, we found out, because normally people talk about magnetic systems as if they are easy axis or easy plane. That means that they are most easily magnetized along a high symmetry axis or perpendicular to a high symmetry axis. But what we found out is that this is not a good classification. You actually need to broaden the idea a lot, because you can also have things like easy cone. And one system is not easy axis or easy plane. It can be both things. So we, for example, with the complexes we saw before, we looked at the erbium and holmium members of this series. And what we could see was at low temperature, the erbium here had the shape here, which means that it is easy plane, and holmium was easy axis, and vice versa at high temperatures. So, and at intermediate temperatures, we could get interesting energy variations with the direction of the magnetic field. So we introduced so-called magnetic anisotropy phase diagrams. Very good postdoc, Mauro Perfetti, did this work. So is this an exotic phenomenon which only applies to the systems we found there? No, actually, when we went back into the literature, we found out that you really need to extract these parameters and understand them. Approximately 40% of all the listed robustly parameterized systems in the literature actually exhibited switching of the magnetic anisotropy as a function of temperature. And this is something, as a function of magnetic field. So this is something you can think about in the context of devices and so on. So you saw Linda Döhr had this dimerization with the platinums gluing themselves together. And those complexes she was working with were neutral. So she only had one of these metallo-ligands on the middle. It was divalent. But if we put two of those negatively charged ligands on to a 4+ center, then we end up with something neutral. So -2 for each of the ligands. So if we take something tetravalent and put it into the middle, we get something neutral. And indeed, we again see this metallophilic interaction between the platinum centers, and we get polymerization. So we have a metallic chain here. And you can see the platinum-platinum distance and the platinum-thorium distance in these systems are very comparable. So we can take this beyond thorium and uranium. So we have also played with the guys in Karlsruhe at the Institute for Transuranchemie, played with neptunium and plutonium, and it all works nicely. And Emil here is played with some slightly more complicated thioacids, and it's been building doubly isolated metallic wires. So in the middle here, you have a chain of alternating actinide and platinum centers, and then you have your first isolation layer, and then you have the third butyl groups really beautifully packing together to give this doubled isolated metallic wire. So Something which is nice about these high symmetry systems is that we can actually study their magnetism and we can understand it. So this is a simulation of the Neptunian platinum 2 system. This is the experiment, and it looks pretty convincing. This is not something which is commonplace for actinide chemistry. The normal situation, more or less, okay. So this is what we measure, and that's it. So, but yeah, so the dices have been thrown, but one final comment about these systems, we could also change the platinum, for example, for palladium. You say, that doesn't make a big difference. But if you look at the EPR spectrum, those two here, which are on the same scale, you see it makes a huge difference, which actually means there's interactions between the platinum or palladium and the central lanthanide. So you could turn this a bond, and I applied and got money for a project named Forging New Bonds, where we try to extend this a little bit more and see if we can force these noble metals onto the hard lanthanides and actinides and make new bonds which are not known in the literature. So I have -1 minute, but I anyway want to acknowledge some of the people who were involved in this. It's especially Mikkel and Mauro who did the platinum lanthanide stuff. It is Jesper who was the driving force in the fluoride chemistry. And then we have absolutely been relying on the guys in Karlsruhe for the trans uranium chemistry. So that was it.